This is EC 201, lecture 30. Last time around, we were looking at ways in which we could bias the bipolar transistor so that the quiescent current becomes independent of the properties of the device, just like how we did for the MOS transistor. The basic idea was biasing the transistor with a constant base emitter voltage is a route to disaster. So we have to use some kind of feedback based technique to stabilize the quiescent current in the transistors. And where we left off last time, put a resistor in the emitter, and how we come to this solution is, we have seen this in the case of the MOSFET, where we try to put a current source and then try to do without a real current source. We try to use a resistor instead, and we need to use a large resistor. And the question now is, what is the definition of large? And what did we see in the MOS case? What is a large resistor? Oh, by the way, what is if the base current is neglected, what is the potential at this node? It is, let me call that VB. VB is nothing but VCC times RB by RA plus RB, and the collector current IC is going to be approximately VB minus 0.65 divided by RE. And why does this make sense? We said that the bipolar transistor is so sensitive to the base emitter voltage that if it's carrying any current at all, the base emitter voltage is approximately equal to the nominal voltage, which is about 0.65 volts. So the drop across the emitter resistance, which is this chap here, is VB minus 0.65 volts. That divided by RE should give the current in the emitter, which should be the same as the current in the collector, simply because the beta is assumed to be very, very large. Okay? And in the MOS case, what did we, having RE is equivalent to having a current source in the emitter if RE is very large. Now, what is large? Large basically means RE must be much, much larger than 1 over Gn. So last time around we did this with the MOS transistor. So we had VA. Assume the collector is going to a very high potential. VB VC let me call this I naught. Further, let us say VA has been chosen to be, in all these three cases, the transistor is identical. The base current is 0, let's say, and we have chosen VA to be equal to that which results in a collector current equal to I naught. So what should VA be? VA must be equal to VT ln I naught by IS. What voltage should I apply at the base in this case so as to have a collector current equal to I naught? It is? Yeah, it's nothing but VA plus I naught RE. Okay. What about VC? It can be anything as long as the transistor is operating in the active region. Please note that the saturation region in the bipolar transistor is not to be confused with the saturation region in the MOS transistor. If I now perturb each of these voltages by a delta V, so instead of having VA, I had VA plus delta V. If I had VB, so if applying VB, let's say this potential changed by a small delta V. So what is, clearly this current is no longer I naught, it's I naught plus delta I. This current is also I naught plus some other delta IB, and this current is I plus delta IC. Now can somebody comment quickly on delta IA? So when VA was applied, the current was I naught. When I apply VA plus delta V, what happens? It will increase. And by how much will it increase? Is approximately, it will increase by GM delta V. So what happens in the third case? Delta IC is 0. Why? Because the current was in the emitter, the current can't change. What about delta IB now? What happens? When you don't know what happens, what do? You replace the transistor by its incremental equivalent. What is the incremental equivalent circuit? This is GM what? Times delta V minus, let me call that Vx minus Vx. And which is delta I? the collector current, the change in the collector current, which is delta IB, is delta I. The reason why there is no resistor in this particular example is because I have assumed beta to be infinite. Now can somebody quickly run through the analysis and tell me what delta IB will be? Delta IB, yes, by RE times 1 over GM, and to standardize it with respect to delta IA, I can write this as GM delta V divided by 1 plus GM RE. To summarize, delta IA is nothing but GM delta V, delta IB is GM delta V divided by 1 plus GM RE, and delta IC is GM delta V divided by infinity. You understand? And clearly from this expression you see the following, which is, as RE tends to infinity, the effect is the same as having a current source, okay, and when RE tends to 0, you have GM delta V. This seems fair, right? What is the function of the current source here? Putting the current source in the emitter is a form of negative feedback where you measure the current in the emitter, compare it with I0 and apply feedback, corrective feedback at the emitter itself. The large resistor, though not quite as effective as the current source, does still give you, there is negative feedback here simply because if this current tries to increase, what happens? The emitter voltage will actually go up, thereby reducing the base emitter voltage, thereby causing the collector current to reduce. Okay, there is negative feedback with the emitter resistor. However, the amount of feedback is not quite as large as you can expect with the current source, and the degree of feedback, okay, or the amount of correction that the feedback loop gives you is indicated by which number? You have the emitter resistor. What number gives you? Looking at these expressions, can you tell me what number represents the strength of the feedback loop? It is GMRE. This represents how strong the negative feedback loop is. And what is the expression for GM of the bipolar transistor? GM is nothing but IC by VT. Alright. So there is a lot of negative feedback if GMRE is much larger than 1, which means what? IC times RE is much larger than VT. You understand? In other words, in English, what does this mean? What is IC times RE? Is the drop across the emitter resistor. So one sure shot way of looking at the circuit and figuring out if it is robust against transistor variations, which is equivalent to saying is the negative feedback loop strong enough, is to simply compare the drop across the emitter resistor with the thermal voltage VT. Does that make sense? So if the drop across the emitter voltage was 1 volt and obviously the thermal voltage is about 25 millivolts, so the ratio is about 40. So GMRE is much larger than 1. So if this potential changes by delta V, the change in the current can be expected to be approximately 1/40th of what it would be if the RE wasn't there. This is exactly analogous to what we did in the MOS case. And once you figure out the bias technique, I'll now leave it to you as an exercise to go and figure out all the amplifier structures. All fairly straightforward. What is the next bias technique? How do I stabilize bias using negative feedback? We've covered 2 of them. The next one is to measure current in the, so we measure collector current and apply feedback at the emitter So we all agree that we keep the base fixed at some potential and we need to compare the collector current with with I naught. Okay. If I naught is greater than IC, what does it mean? What will happen to the potential of this node? If I naught is greater than IC, it means that the potential of this node, it will go up. But I naught being greater than IC basically means the emitter is too high or too low. If I naught, if IC is too small, it means VBE is too small. VB is fixed. VB is fixed. So E is too high. So I must go and yank the emitter down. So basically, and the only way the 2 of them will be equal will be when this node, the collector tends to sits at a constant potential. So one way of keeping everything in check is to fix this to some reference, compare this potential with the potential of the collector with the reference and go and if this voltage is rising, I must decrease the emitter potential. So what must be the signs of the op amp? Minus, plus. How should I choose Vref in relation to VB? I want to choose, to keep the transistor in the active region. Vref must be greater than VB. The collector must be higher than the base. The lowest the collector can go to without the transistor getting into the saturation region is the base voltage. And once the bias technique is known, it is in fact quite trivial to kind of make sure that the op amp doesn't create any mischief for incremental signals. So one thing you could do is, for example, put a resistor Rx which is very large. If you want to make a common emitter amplifier, that is. What else do I need to do? I need to put a big capacitor here. Alright. So I need to bias this voltage without recourse to another voltage source. So RA, RB, I need to apply an input. The infinite capacitor, another infinite capacitor, and RL. You understand? The question is, do you really require Rx after all? Please note that the op amp, an ideal op amp is equivalent to a voltage controlled voltage source. So this voltage will still be jumping around in response to a variation in voltage here. But in practice, if this capacitance is finite and the op amp behaves indeed like an ideal voltage controlled voltage source, then this voltage will jump around. So without the Rx, the emitter will jump around when the collector moves. Ideally, you want the emitter potential to be a DC voltage which doesn't move at all. But if the op amp will truly behave like an ideal voltage controlled voltage source, without the Rx, if the collector moves, you will find that this will also move, even though you have a big capacitor. That's the definition of a voltage source. So you must, in other words, you must screw up the ideal nature of the voltage source, which is what Rx does. The next thing, the last generic technique to bias is measure the current in the emitter and apply feedback at the base here. We assume that the collector is fixed to some voltage, say VCC. We compare the emitter current to I0, and we basically are interested in fooling around with the base voltage. If the node potential here increases, what does that mean? It means that the collector current is too much, which means what? The base voltage is too high, which means I must reduce VB. So I compare this with some constant voltage Vref. This potential is increasing, I must reduce VB. So what should be the sign of the op amp? Which should be plus, left or right? Left should be the plus sign, right should be the negative sign. And if redrawn the way it is in the textbooks, it will look so. What is this potential? This potential is Vref. So how would I choose Vref to make sure that the transistor is operating in the active region? What is the potential of the base? Approximately, it is Vref plus 0.65 volts this potential is Vref plus 0.65 volts, which means to keep the transistor active, Vref plus 0.65 volts must be less than the collector potential, which is VCC. Again we notice that you can bias the transistor this way and then add resistors, capacitors here and then, make sure that it does whatever you want for incremental operation. So that kind of finishes the discussion on bias stabilization. The bottom line in all these discussions is the following, that if the transistor is operating in the active region, the transistor is basically a voltage controlled current source, and fundamentally, is there any limit on the transconductance of the PCCS? In principle, there is no limit on GM, because GM is of the form IC by VT. So by going on burning more and more current, in principle I can get as large a GM as I want, just like in the MOS case. You understand? Any amplifier that I make with a VCCS will have a gain, impedance, which are all dependent on the transistor. Okay, it's a VCCS, and to remind you of the incremental model, this is beta times VT by IC. This is GM VBE. This is RO. This is the base, this is the collector, this is the emitter. The VCCS is not as ideal a VCCS as you want, because what is the input impedance of an ideal voltage controlled current source? Infinity. Here you see that it tends to infinity only when beta tends to infinity. And of course, as usual, the current source is not ideal either. There is some output impedance associated with the current source. So if I made a common emitter amplifier, for example, we see that the input impedance, the output impedance will all depend on these quantities, the beta as well as VT. In other words, we can now get in principle an amplifier with as large a gain as we want, but this gain will be dependent on device parameters. And just like what we did for the MOS case, the next step is to derive all the four control sources, where the control parameters, either the the voltage gain or the transconductance or the current gain or the trans impedance, all are set by feedback, because you know that when you have block where the gain is very large but uncontrolled, you can always put it as a forward amplifier in a feedback loop and make the input-output behavior of the feedback system largely independent of the forward amplifier itself. And we kind of derived everything for the MOS transistor case, so I am not going to go through the stuff in the same excruciating detail as I did there. I will just zip through it. I guess most of you must now be familiar with the whole stuff. The first thing is the voltage controlled voltage source. Let's try and get a gain of 1. So we need V out to be equal to V in. And what are the attributes of an ideal voltage controlled voltage source? Z in must be infinity, Z out must be 0. In other words, regardless of the value of the load resistor I put at the output port, the output voltage must be the same as the, so assume these are all incremental signals. So let me make this, V out must be equal to V in. Please note that like in the MOS case, we are interested in an incremental voltage controlled voltage source where we want V out to be equal to V in. All that we have is a voltage controlled current source with in principle an infinite gain. What will I do if I were in a lab and I wanted to make this potential equal to this potential? I will compare these two. If V out is too small compared to V in, I will try and push up the potential of this node. And how will I push up the potential of that node? I will pump a current into this node. And this current source here must be dependent on the difference between the voltages at this V in and at V out. Correct? So it must be of the form Gm times V in minus V out. Is the sign correct? Yes, because if V out is smaller than V in, you want current to flow into that node. Okay, so the sign is okay. And when steady state is reached, you want there to be no error between the output and the input. So in principle, this Gm must be very, very large or infinity. What do you identify with as a transistor? You already know a device whose incremental equivalent looks like this. This guy here. Except that, what is missing? The resistance between the base and the emitter is, incremental resistance is missing. Okay, that basically assumes that the beta is infinity. You understand? So which is the base, which is the emitter, which is the collector now? This is the base, this is the emitter, the collector. You understand? So topologically, the incremental equivalent circuit looks like this. This is Vi, this is Vo. What do we see here? The collector is common to both the input circuit and the output circuit. So this incremental picture is that corresponding to what is called the common collector amplifier. The next thing is to, in painful detail, work out the various things when Gm is not infinity, okay, and when beta is not infinity. So this is a little more painful than what we were used to in the MOS case, but we should do it anyway. This is beta times Vt by Ic, alright, which is beta by Gm. Vt by Ic is nothing but 1 over Gm. This is Gm VBE. The collector is grounded. You have RL V out. This is Vn. How would I figure what V out would be? Incremental VBE is nothing but Vin minus V out. Another way of looking at it is, if this current is I, this current will be beta I. I mean, they are all equivalently the same thing. Tell me how I'll be able to calculate V out in terms of V in. Right, Kirchhoff's law at that node. So what is Kirchhoff's current law here? V out times GL, which is 1 over RL. That's the current flowing in this direction. Must be equal to V in minus V out times Gm by beta, which is this current here. What is this current? Plus Gm times V in minus V out, which means V out times GL plus Gm by beta plus Gm, okay, which is obtained by moving this chap and this chap to the opposite side of the equation. This must be equal to V in times Gm plus Gm by beta. So V out by V in is given by the following expression. It is Gm times 1 plus 1 by beta divided by Gm times 1 plus 1 by beta plus, what do you observe from here? As Gm tends to infinity, V out by V in tends to 1, as we expected. Obviously, Gm tending to infinity is not a practical option. So, the next thing to do is to say, if Gm is large, V out by V in is approximately 1. The question is, what is the meaning of large Gm? I mean, beta is a large number anyway, so 1 by beta is very small compared to 1. So, large means Gm is much larger than GL, which is equivalent to saying Gm RL is much larger than 1. This is exactly the same condition we derived earlier when you had the RE biasing in the emitter. Think about it carefully and you will understand why this result must make sense. You have a voltage controlled voltage source, you are interested in the gain, you wanted 1, we got something close to 1 provided Gm is sufficiently large. The next thing to evaluate is the input impedance. So how will I find the input impedance? Is the incremental impedance looking in here. So what should I do? I apply a voltage, find the current, or push in a current, find the voltage. What do you think is the more convenient thing to do here? Push in a current. Why? Look here, stuff is in series. So it's always, when things are in series, it's always easy to push in a current because the current will flow through all the branches. So let's try and put a test current source like this. So if Ix flows here, I must flow the same I must flow like this. If this is Ix, what is this current? Beta Ix. Okay, so what is this current? Kirchhoff's current law, it must be beta plus 1 times Ix. Is that clear? So what is the voltage developed? Vx here. It's nothing but the potential drop across this resistor, which is beta plus 1 times RL times Ix plus the potential drop across this chap, which is beta by Gm times Ix. Okay, and that must be Vx, which means the input impedance is nothing but Vx by Ix, which is beta plus 1 times RL plus beta by Gm. And clearly you see that as beta tends to infinity, Zin tends to infinity. And that makes sense, right? As beta tends to infinity, this resistor itself goes to infinity. So what is RL? RL is the impedance of the emitter. Okay, Zn is the impedance at the base. So the impedance at the base is getting multiplied by a factor beta plus 1. And why does that physically make sense? See this, you can think of it in the following manner. If you had a current controlled current source, let's say this was I and this was beta I, then even though you inject only a current I from the input, the total current flowing into this resistor is beta plus 1 times I. So the voltage drop across this resistor will seem is beta plus 1 times larger than what you would expect if only I had flown through it. So it will seem as if the impedance has gotten multiplied by a large factor. The last thing to figure out is what the output impedance is. So if I need to find the output impedance, what should I do to the input? I should incrementally ground it. And how will I find the output impedance? I could apply a current, measure the voltage, or apply a voltage, measure the current. So what do you think makes sense now? Apply a voltage because branches are all coming in shunt. If I apply a test voltage to find the output impedance, I don't need the output resistor, the load resistance anyway. I apply Vx, measure Ix, and if I apply Vx, what is the current flowing like this? Ix is nothing but Vx times Gm by beta plus Gm Vx. So this output is nothing but Vx, the input is nothing but ground. So I could have, for instance, changed the direction of this current source and made this plus Gm Vx, which means the output impedance is 1 over Gm times 1 plus 1 over beta. Beta is typically a large number, 50, 100, that kind of thing. So the output impedance is 1 by Gm. And as Gm tends to infinity, Z out tends to, you understand? As beta and Gm become larger and larger and larger, we see that the common collector amplifier behaves like an ideal voltage controlled voltage source with an incremental gain of 1, input impedance of infinity and an output impedance of 0. Obviously we cannot achieve infinite Gm. So the next thing we say that if you have a large Gm, then we'll approach these conditions. And what is large Gm? There is nothing absolutely large or small. When I say large Gm, I mean that GMRL must be much larger than 1. Okay, so we'll stop here.